Hello, a great welcome to this presentation on the design of beam-to-beam end plate shear connections. Here I will present a sample calculation to demonstrate the various steps required for performing this calculation. All the verifications are performed as per the Eurocode EC3 norms. So before starting with this sample calculation, let me provide you a brief introduction about this connection. Here is presented a 3D view of the connection. It is clear that it consists of three components: a supported beam, an end plate, and a supporting beam. Based on the depth of the end plate, the connection can be either a partial depth or full depth. So the connection essentially consists of an end plate that is sharp welded to the supported beam. The supported beam is then bolted to the supporting beam on the site. Here is presented a comprehensive list of verifications required to perform the design of this connection. It starts with check 1, that it to see is compliance to the recommended detailing practices. Check 2, computing shear capacity of supported beam web at the end plate. Check 3, verifying the moment capacity of supported beam at the notch. Check 4, verification of bolt group. Check 5, verification of end plate. And finally, the calculation concludes with the verification of welds. So all the calculations are done using the two basis documents, that is EN 199311, that is the first part of EN 1993, design of steel structures, general rules and rules for buildings. And the second document, EN 199318, that is for the design of joints. So majority of the provisions are taken from the second document. Okay, fine. So let us start with the input parameters for the problem. So here is shown the sketch for the example problem. It is very clear that the supporting beam is IP360 and the supported beam is IP300. And here we have an end plate which is of dimension 220 by 150. So here is presented the section properties. Obviously we have two sections, that is one for the supported beam, that is IPE300, and the second for the supporting beam. Here for the supported beam, all the parameters are identified using a subscript 1, whereas no subscript is used for the supporting beam. Accordingly, as you can see that for the supported beam IP300, the depth is indicated through H1, that is 300 mm, whereas for the supporting beam, H is used without a subscript, that is H is 360 mm. In a similar way is presented here the flange width, the flange thickness, web thickness, root radius. All these are the section parameters. Then the depth of notch, it is very clearly marked over here, because to clear the flange we have to make a notch over the supported beam, and the depth of notch HN is taken as 50 mm. The length of the beam notch, that is clearly marked over the sketch as, that is 80 mm. And the yield stress for both the beam materials is taken as FY 275 mm. The partial safety factors are taken as gamma MO1 and gamma M2 as 1.25. Obviously we know that gamma M2 is normally used for computing the resistance against rupture or the bolt resistance. So next is provided the parameters associated with the end plate. As you can see that the width of the plate is 150 mm, so it is 90 plus 60, 150 mm. And we have the height of the plate HP, that is 220 mm. The thickness is taken as 10 mm. And the yield strength and the ultimate tensile strength of the plate, these are taken as per table 3.1 of EN 199311. Accordingly, we have the yield stress as 275 MPa and the ultimate tensile strength of the plate material is 430 MPa. So that's all about the end plates. Now let me provide you some of the parameters associated with the bolt and weld details. As is clear from the sketch, the total number of bolts that is used is NB6. Diameter of the bolt is 20 mm, and the bolt diameter is taken as per table 11 of EN 10902, that is D0 for D20 mm bolt is D0 22 mm, and the edge distances E1 and E2. So remember, E1 is the edge distance, that is 40 mm in the direction of the load, and E2 is again another edge distance, but it is perpendicular to the load. So this is my E2 30 mm. And all this minimum requirement of the edge distances can be directly obtained from table 3.3 of EN 199318. Now coming to the gauge distance, P3 is taken as 90 mm. Gauge distance means the distance between the two vertical rows, that is 90 mm. And the distance between the bolt rows, P1 is 70 mm. So this is 70 mm. And the coefficient for the bolts, alpha V, this is for the shear capacity calculation, is taken as 0.6 as per table 3.4 of EN 199318. And the stress area of the bolt, that is normally taken as AS, is taken as 245 mm square for the M20 bolt. Now there are some more parameters associated with the bolts as well as the welds. And regarding their strength, the ultimate tensile strength and the yield strength of class 8.8 bolts that is used for the calculation is taken as per table 3.1 of EN 199318. Accordingly, the yield stress for the bolt is 640, whereas the ultimate tensile strength is 800 MPa. The weld size is taken as 6 mm, and the ultimate tensile strength of the parts joined by the weld, it is FUW, is taken as 430 MPa, and the correlation factor beta W, this is used for the verification of the weld, is taken as 0.85. The applied load, that means the entire connection will be checked for an applied load which is applied shear, which is indicated as VED is equal to 200 kilonewton. That is, the supported beam IP300 transfers a shear of 200 kilonewton to the supporting beam, and all the components will be verified for this applied load of 200 kilonewton. Okay, fine. So let us start with check 1, that is to see whether it conforms to the detailing practices. And normally 2 checks are performed. One is regarding the depth of the end plate. For example, here we know that the depth of the end plate is 220 mm, and this needs to be greater than 0.6 times the depth of the supported beam. Obviously, we know that 0.6 times H1 is 180 mm. That is, the depth of the end plate is higher than 180 mm. So it does mean that the assumed pile, the plate depth, that satisfies the normal detailing practice. And the second check to be performed is regarding the throat size of the weld. We know that the weld size assumed W is 6 mm, which means that the corresponding throat size will be 8.7 times of W, that is 4.24 mm. And this throat size should be greater than 0.4 times the web thickness of the supporter beam, that is 0.4 into 7, that is 2.8 mm. So we find that this calculation, all the parameters or the dimensions of the plate or the weld, it follows or it conforms to the normal detailing practices. Fine. So let us start with the second check, that is verifying the shear capacity of the supporter beam at the end plate. What does it mean? Look here. This is how the supporter beam is connected to the end plate. So we need to calculate or we need to verify whether the beam web has sufficient shear capacity at the end plate connection, which means that the depth of the beam web that is used for this verification will be obviously the depth of the end plate. Accordingly, the shear capacity of the beam web at the end plate will be computed as VRD. This is a standard expression used in the Eurocode. 0.9 times the area of the web. Obviously, we know that the area of the web in this case is HP, that is the depth of the end plate, into TW1 into Fi1 by square root of root 3 gamma MO. Substituting the various values, we find that the shear capacity of the beam web at the end plate is 220.06 kilonewton, and obviously this is higher than the applied shear of 200 kilonewton. Hence, we have satisfied check number 2. Now let us proceed for the check 3, that is computing the moment capacity of the supported beam at the notch. What does it mean? So here is shown the supported beam along with the notch, and we know that the applied shear is provided at a distance d from the notch, which means that we need to verify whether the supported beam has sufficient moment of resistance at this critical section of notch. So as you can see that if you take a cross section of the supported beam at the notch, it will have a T section, which means that as per the normal practice, we need to first of all obtain the section modulus of this T section, and then multiplying it with the yield stress, we'll be able to obtain what will be the moment of resistance of the supported beam. So here is the detailed calculation. First we calculate the total area of the T section at the notch section. That means what will be the total area. Now because we have all the parameters, like for example the flange thickness, flange width, web thickness, etc. Substituting these various parameters, you obtain the area of this T section as 3323 mm square. Now this is the total area. Let us calculate what will be the shear area of this T section. Obviously it includes the web plus a part of the root section, and we can obtain the shear area as AVN as the total area minus B1 into TF1 plus TW1 plus 2R1 by 2 into TF1. Substituting the various values as shown here, we obtain the shear area of the T section as 1876 mm square. From the shear area, we can readily obtain the shear capacity of the beam at the notch. So we substitute the shear area of the beam at the notch and obtain the shear capacity as 297.93 kilonewton. Obviously, we find that this capacity is much higher than the capacity of the web that we calculated at the end plate. And remember, the purpose of making this calculation of the shear capacity is to calculate properly the moment of resistance, because as per the Eurocode, the moment of resistance depends upon the level of the shear force applied. That means whether it is a high value of the shear force or a lower value. Now let us proceed as usual to obtain the moment of resistance. So first we obtain the neutral axis of the T section, that is the location Z. This can be directly obtained using our standard formula A1 into x1 bar plus A2 into x2 bar divided by total area. Substituting the various parameters, we obtain the location of the neutral axis of this T section Z as 68.43 mm. Having obtained Z, we can readily proceed for the calculation of the moment of inertia and next to the section modulus. So check 3 is continued. So we obtain now the moment of inertia of the T section at the notch about the neutral axis, and substitute the various parameters. We obtain it as 209.60104 millimeter raised to 4. Now from this moment of inertia, we can readily obtain the elastic section modulus of the T section at the notch, that is for this section, as WELN as I by Y max, that is 115440 millimeter cube. Now having obtained W, that's elastic section modulus, we can readily obtain the moment of resistance of the section based on the consideration of the low shear resistance. That is, if the low shear condition is satisfied, the moment of resistance of the beam section at the notch will be MLN, that is Fy1 into WELN divided by gamma MO. Substituting the values, we obtained as the moment of resistance 31.75 kilonewton meter. Now let us see whether our moment of resistance comes under the low shear or the high shear condition, and this can be readily checked using the clause 6.2.8 of EN 199311. So a high shear condition is obtained when the applied shear VED is greater than 50% of the nominal shear capacity. So in our case, this is satisfied. This condition is satisfied So accordingly, we have to use the moment of resistance calculation corresponding to the high shear calculation, and this is done using this formulation. That is, moment of resistance would be the moment of resistance corresponding to the low shear condition, which is need to be reduced by 1 minus 2 VED by Vn minus 1 the whole square. And performing this calculation, we find that the moment of resistance of the supported beam at the notch section is equal to 28.02 kilonewton meter. So let us verify whether this moment of resistance is good enough to resist the moment due to the applied load. Obviously, the actual moment acting at the notch will be the shear force VED into Ln plus Tp. Obviously, we know that Ln is nothing but the notch width plus Tp, the thickness of the plate. And accordingly, due to VED, the actual moment coming at the notch will be 18 kilonewton meter, which means that our computed moment of resistance of 28.02 is higher than 18 kilonewton meter. Hence, we verify that the notch section is good enough in order to withstand the moment due to the applied shear VED of 200 kilonewton. So that's all about check 3. Obviously, check 3 is a little bit exhaustive, but it is very quite simple. Now let us proceed for the check 4, that is verification of bolt group. As usual, we know that whenever we have the end plate connection, the shear capacity of the bolt will be governed by two actions. One, the shear resistance of the bolt, and second will be the bearing resistance of the bolt against the end plate. Now we can obtain the shear resistance of the single bolt using table 3.4 EN199318, according to which FVRD is alpha into AS into FUB by gamma M2. Remember here alpha is 0.6 and AS is the stress area, that is 245 mm square. And this provides us the capacity of the bolt in single shear as 94.08 kilonewton. Now we need to obtain the bearing resistance of the bolt against the end plate, and this is done again using the expressions given in table 3.4 of EN199318. And here we have two coefficients, K1 and alpha B. K1, as you can see, that it need to be performed in a direction perpendicular to the application of the load. And the coefficient K1 is obtained as minimum of 2.8 into E2 by D0 minus 1.7, 1.4 P3 by D0 minus 1.7, 2.5. Remember that all these parameters, E2 is this 30 mm, and then this is P3. P3 is nothing but it's the gauge distance, means that all these are dimensions perpendicular to the load application. And K1 we obtained as 2.12. And similarly, coming to alpha B, it's a similar coefficient, but it is applicable to the dimensions in the direction of the application of the load. Accordingly, you will find that this expression for alpha B contains E1, that is your 40 mm. And also it consists of P1, that is the distance between the rows, that is 70 mm. And we find alpha B as 0.606. Finally, having obtained these coefficients, we can proceed for the calculation of the bearing resistance of a single bolt as K1 into alpha B into FU P, that is the ultimate tensile strength of the end plate, into dB into TP by gamma M2, that is equal to 88.32 kilonewton. So we have shear resistance and a bearing resistance. So how do you obtain the final resistance? So here we make a comparison between the bearing resistance and 0.8 times the shear resistance, and whichever is governing will be the final resistance of a single bolt. In our case, we find that it will be, so for example, the first condition, it is satisfied. So we find that FBRD is less than or equal to 0.8 FVRD in our case, that is a 451.58 kilonewton. Thus we find that the resistance of the group, look here, from the single bolt, to obtain the resistance of the group, we have to simply multiply the single bolt capacity by the number of bolts NB. So finally we find that the resistance of the bolt is 451.58. This is much higher than the applied shear of 200 kilonewton. Hence, the bolt group is sufficient. So next we go for check 5, that is the computation of the end plate. That means whether the end plate thickness is satisfactory or not. So here, as far as the end plate is concerned, we need to make 3 verifications. One along the cross section, that is identified through section 1.1, and then the capacity of the plate need to be obtained also through the considering the net section, that is as identified through section 2. And finally, we need to check the plate for the block shear which happens along the shaded area. So first we shall proceed for shear resistance of the plate based on the cross section, that is along section 1.1, and this can be obtained using VRDG is equal to 2 into HP TP into FYP divided by 1.27 into square root of 3 into gamma MO. All these expressions are very clear. We are checking the yielding of the plate, and remember the coefficient 2 is here because we have got 2 cross sections on each side of the beam web, and the shear resistance of the plate is obtained as 550 kilonewton. Next we shall proceed for computing the shear resistance of the plate along the net section, that is along section 2.2, for which we need to obtain the net area of the plate, that is obtained as HP into TP minus of NB by 2 into D0 into TP. And this works out to be 1540 mm square. And finally, we compute the shear resistance of the plate along the net section as 2 into AVNP into FUP by square root of 3 gamma M2. Remember here again, 2 means we have got 2 net sections on each side of the beam web. And this works out to be 611.7 kilonewton. Next, we shall proceed for the block shear check. And here, please remember that the block shear has got 2 areas. That is one area that is in the yielding and the other area in the rupture. The area in the yielding will be the area along the vertical edge, and the area for the rupture calculation will be the area corresponding to the bottom edge. And the relevant areas are provided over here. For example, in the shear yielding, we have the area of 1250 mm square, and in the rupture, obviously, we'll have a lesser area, that is 190 mm square. And now the block shear resistance is computed by adding up the capacity of the plate through yielding along the vertical edge and rupture along the horizontal edge. And this works out to be 527.65 kilonewton. And this is obviously very much higher than 200 kilonewton. Hence, this check is also satisfied. So finally, we are at the last step, that is check 6. That's a verification of the welds. Though Eurocode provide you 2 procedures for the verification of welds, I have adopted the simple procedure used here. And the design shear strength of the weld need to be calculated, and this can be done using clause 5.3.3 of EN 199318, and according to which FEWD is calculated as FUW by square root of root 3 divided by beta W into gamma M2, and this is 233.66 MPa. Next, we proceed for calculating the design resistance of the unit length of the weld, and this is obtained by multiplying the design shear strength by the rod thickness, and this is calculated to be 991.32 kilonewton per meter, that is nothing but it's a Newton per millimeter. Therefore, we can obtain the total design resistance by multiplying this design resistance per unit length by the total length of the weld. So the effective length of the fillet weld can be obtained as 2 into HP minus 2A, because for every side of the weld we subtract 2 times the throat thickness for the calculation of the effective length of the weld, and here 2 means we have got 2 welds on each side of this beam web. Finally, we obtain the total design resistance as 991.32 multiplied by 423, that is 419.36 kilonewton, and this is much higher than 200 kilonewton. Therefore, the weld verification is also passed. So that's all regarding this presentation. So as usual, please go ahead and subscribe. If you have any comments, please let me know, and all your opinion for the improvement of this series will be of great help in future. So thanking you once again, and have a nice day.